All right. Hello, welcome, Physics 122 students. Let me work out some examples from Chapter 33. These are the ones I was talking about in class that I would work out a video. Let's do these four together, and then I'll do a second video with doing the next four. So I'll begin this video then by saying, all right, let's do Chapter 33. Let's start with number 7. I printed up hard copies of it, and it says here in a purely inductive AC circuit as shown. So they shown in figure 6, purely inductive looks something like this. All it has is one inductor. That's it. No resistor, no capacitor. This is an early problem in the chapter, so nothing too complicated here. And when we did the full set of the current with the resistor and a capacitor, we got voltage divided by the impedance, where the impedance was the total effect of both the resistor and the capacitors. Oh, and the inductor. But for us, because we have no resistor and no capacitor in this very simple one, it just boils down to this: voltage divided by the reactance of the inductor. In other words, the whole impedance is only in inductance here. And so when they say, and here's kind of maybe a little carefulness of the problem, maximum current, we can come back to this and say, all right, maximum current goes with maximum voltage. Now, we could do RMS with RMS also, but I'm going to match up maximum with maximum, because in this problem they give me maximum voltage, and they even then give me the maximum current, and then they give me the frequency. And that's what I need for the reactance of the inductor. So the maximum current, they say, is 7.5 amps, okay. The voltage, they say, maximum is 100 volts. The frequency, and really this would be the angular frequency, so omega is 2 pi times what I'll call the regular frequency, so that's 50 hertz. And by the way, most of our international frequencies, you guys have heard me say many times that in North America the frequency is 60, and you should keep that in mind. But in many other places of the world, I'll say Europe, and I believe Asia also, they operate their grid at 50 hertz. So a little different number, but that kind of explains where that number kind of probably is coming from. We're plugged into a circuit, say, in Italy or something, and that'd be the 50 hertz. Okay, and then the L, calculate the inductance, is what they're asking for here. And so that's the unknown. So L then becomes the 100 in the numerator. I'll put the 2 and the 50 together, so that becomes 100 pi divided by 7.5. I'll even cancel off the 100s to save me a little calculator work. And now I have 1 divided by, looks like first factor is a pi, and the other factor is 7.5 from the amps, and it looks like a 0.042 for Henry inductor, or maybe I'll write it as 42.4 millihenry inductor. And so there's the first part of it. Now, B says, what if? What would be, excuse me, at what angular frequency, omega, is the current now reduced? And maybe talking about concept a little bit, remember our Faraday's law here is that the reactant of this capacitor is caused by Faraday's law, which says it's proportional to the rate of change. So the higher the rate of change, the more opposition, and so in other words, Z, or the impedance, gets greater, and because of that, we get less current. So this is going to be at a higher frequency. In other words, to reduce this current down by a factor of 3, we're going to have to increase our frequency. And you can see it's linear, so it would be a factor of 3. So I guess we're looking at 150 hertz. Although maybe I'll just run the numbers here so that you can kind of see, other than me doing proportions. But here is the starting equation, and so now we're going to be down to 2.5 amps. The voltage is still going to be 100, and then this right here is still the omega, so 2 pi f, and the inductance is this 0.0424, and now solve for f. So I'll bring f over to this side and bring the 2.5 over to here. So on my calculator, this is going to be 100, I guess divided by a 2, I guess divided by a pi. Another division is what I bring over, the 2.5, and then the 0.0424, and we're looking at, like I said, 150 hertz. So reduce the current by a factor of 3, and since it's linear, you increase the frequency by a factor of 3. All right, so hopefully that one wasn't too bad of a problem. Let's move on then to number 10. So number 10 says that we have a 20 millihenry inductor, and it is connected to a standard electrical outlet. Now again, standard electrical outlet, I think they mean in North America, and the RMS voltage is 120 and the frequency is 60. All right. Determine the energy stored in the inductor. This is a good one. At 1/180th of a second, go ahead and assume that the energy is 0 at time equals to 0. All right. So I'm going to start with the equation that we worked out for the energy in the inductor. And this is 1/2 L I squared. And so because the current changes with time, so I'll say current as a function of time, then you're going to have the energy that changes as a function of time. And so now maybe the question makes a little more sense, that determine the energy stored in the inductor at this moment in time. So they give a specific moment in time because, again, since the current changes with time, so also will be the magnetic field, which is where the energy is stored. Okay, so really this kind of boils down to figuring out the currents at that moment in time. And that current at that moment in time would be some maximum, and it would be sine omega t. And I'm going to throw in a little phase here, because when you have current that changes with time, and so I'll do a little graph of current and time. Actually, I just noticed I think my red stands out a little bit better. So let me jump back here to the red. Hopefully that won't mess you up too much. But as it goes up and down, oscillating in time, we could, define time equals to 0 kind of anywhere we want. So we could maybe put the grid there, and then we would have a negative cosine function, or we could put the grid here, and then we'd have a positive cosine function. And so this phi is what determines whether or not this sine is the equivalent to a negative cosine, or to a cosine, or to a negative sine, or something in between. So in general, that's just kind of a loose variable. But if you'll notice, they did something quite interesting. They said, assuming that the energy is 0 at time equals to 0. So this was their way of saying at time equals to 0, the current is equal to 0. And that happens when phi is 0. In other words, there's no shifting in the sine function. So, as you already probably know, a sine function looks like this and has 0 current at 0 time. So, you might say that, well, having this discussion about phi is not relevant. Well, it could be important for another problem, because how you define time equals to 0 could vary from problem to problem. Now, luckily for me, that if I was careless and didn't think about this phi and said it was 0, it would work out this time because I have a phi equals to 0. But I need to justify that, and that's what this is doing. The other reason I say that, because if you look at the equation derived in the book, the author takes a different approach and says that the voltage is 0 at time equals to 0. And I believe the author then comes up with a negative cosine function for the current. Or he writes a negative I maximum, then he writes it as sine omega t minus pi over 2. So he doesn't write the negative cosine, he writes it as a sine, oh, sorry, there'd be no plus there. He writes it as a sine that has been shifted, because if you take a sine function back here, and let me extend it over, and you shift the grid, so I'll shift the axis by a negative pi over 2, you get a negative cosine function. So if you just follow the equations in the book, if you just blindly follow them, they're going to be wrong, because they're based upon something defining time a little different than in this problem. And so that's why it's important to recognize right here your author's definition of time equals to 0. In fact, it makes me kind of second guess myself. So I'm going to grab the textbook here. Let's see. Here's where he does a resistor. Here it is, I believe. So here's where he does the inductor. It looks like in section 3 he says the inductor, and he goes through here. Right here. See, here he says the voltage is a sine function. But then the current is related to the derivative of that. And so solving this equation, he says the current equals, and there he has it, a negative cosine function. Or the current is a sine function shifted by a pi over 2. So if you were to use that equation, which is the same as this equation, it would be wrong for this problem. It doesn't have the right starting of time equals to 0. So that's kind of a big reason I wanted to point that out. Also, because you just never know how a particular author or a particular problem is going to define its 0 point. And that's why that was such an important piece. Okay, so knowing that, I guess I then have this. I, as a function of time, is equal to I maximum sine omega t. Okay, and so coming back over to here, I can use the equation that we did in the last problem, that if you take the maximum voltage and you divide it by the impedance of that particular circuit, you will get the maximum current. Now, we could put RMS with RMS, although we could also put maximum with maximum, and I think I'm going to do that because I want to know the maximum. Although I'm also tempted to look at RMS because they give me RMS. So what do I do? Somewhere I got to use both. So maybe I'll do it this way. I will say that the maximum voltage is the RMS of 120, then multiplied by the square root of 2. And then when it comes to the impedance, since we just have an inductor, write out the complete impedance to get me started. But for this problem, I can say, well, I have no resistor and I have no capacitor. And so all I end up with is XL down at the bottom. And this 120 times the square root of 2 is that 170 we looked at. It's probably worth recalculating it. 120 times the square root of 2. Yeah, well, 169.7. I'll call it 170. All right, so this is saying 170 divided by 2 pi f. And, maybe I'll just put in the value of f. We're told it's a standard circuit in North America, so that's 60. We're also told the inductance, which is the 20 millihenries, okay? And so this will allow me to get the maximum current. And so 170 divided by, and I'll just put the 2 and the 60 together, that's 120. I'll divide also by pi, and I'll also divide by 0.020 for the millihenries. And so we're looking at about 22, and I'll go at 5.5, take an extra significant figure for the moment. So 22.55 amps that, of course, would fit into this equation, and it would then be doing something like this when we talk about the current as a function of time. Now, another thing that I got to be sure about, which goes back to the very beginning right here, is now I got to figure out what that what the current is at that particular moment. So let me say, all right, what is the current at, what did they say? What moment in time? 1 over 1/80th of a second. So it'd be this maximum, 22.55 times the sine of, and omega would be 2 pi times 60. And then the time would be 1 over 180. Is that any of the special trig functions? Looks like I've got 120, which is divisible by 60. And so is 180. So that would be 2/3 of a pi. Oh, that is one of the magical ones. That's equivalent of 60 degrees, which is what? √3 over 2, which is about 0.866, I believe. I better not guess here. So let me grab my calculator here. And let me check the mode in my calculator. Okay, let me make sure that I'm in radians, which I am not. So let me do that. And so let me look at the sine of 2/3 of pi. Yeah, 0.866. Okay, good. So that's the √3 over 2. And then times this maximum, and that's a 19.5 amps. All right, so 2/3, coming back to this graph, let's see, this right here is pi over 2, and this is pi, so 2/3 is right about there. So in this particular problem, the current has, gone up first to its maximum and is now heading on its way down, and is just below its maximum of 22.5, a little bit below that at 19.5. But now we can do the last part and perhaps the easiest part of this, which is to say that it's 1/2 Li squared. So 1/2, and I will put the 20 millihenries at 0.02 and the current as 19.5 amps and square it, and now I'll get the current. In fact, I already have the square in there, so let me just already have the current in there. Let me square it and then multiply by 0.02 and then multiply that by 1/2. And we're looking at about a 3.81 joules of energy in that inductor at that moment, because it has the 19.5 amps, again, at that moment. All right, well, there's number 2 here. Hopefully that was somewhat helpful. Let's try the third one on my list. What was my third one here? Oh, yeah, number 15. Okay, so here's number 15. Let's read it here together. And so 15 says, what maximum current is delivered by an AC source with a maximum of 48 volts, a frequency of 90 when connected across a capacitor? So this is a lot like the last two we were doing, except we've now replaced the inductor with a capacitor. But either way, maybe the best way to explain it is to jump right to the full set where the impedance is all three, the inductance, the capacitance, and the resistance. But for this case, there's no point in talking about the resistor, and there's no point in talking about the reactance of the inductor. So I'll cross that out and cross that out. And so what I get is V over XC. All right. And we can then put in, and this is where I'm going to say again, if we're hunting for maximum current, we would put in maximum voltage. If we were hunting for RMS, we would match RMS voltage with RMS current. Or we can find the maximum and then divide by square root of 2. That's how you can get the RMS. So they match there. That's why a lot of times we don't write something down below, because we know it works for RMS as well as maximum. But once you pinpoint the particular problem, and in this one, what maximum current and the voltage maximum, I'll put maximum with maximum. So this maximum voltage is 48 volts, and the reactance is 1 over omega C. I don't know if you want to separate or calculate that on its own. Maybe I will. And so the reactance is 1 over omega C, which would be 1 over 2 pi F. What was F again in this one? 90 hertz. So here's 90 hertz. And the C is a 3.7 microfarad capacitor. Okay. So I'll just go across the bottom. 2 times pi times 90 times 3.7 times 10 to the negative 6. So there's the denominator. Take the reciprocal of that, and it looks like 478 ohms. So 478 ohms would be the impedance. Well, yeah, it would be the impedance, but I should just call it the reactance of the capacitor, since that's all we have for this particular problem. So in this case, the impedance and the reactance of the capacitor are one and the same. All right, so now I can use that up here. And it looks like they tried to make this about 480 to cancel off with an even number here. So 48 divided by 480. I'll just kind of save myself a little bit of calculator work and realize that 48 goes with 48, and you're left with 1/10, which is 0.1 amps. Or maybe a little more accurate, 48 divided by 478 is that's still to 3 decimals is still just 0.1. Okay, so there is the current. Okay, good. And let's do one more on this video, and it looks like 29 is the fourth one on this list here. It says, in a certain series RLC circuit, the RMS is 9 amps, the voltage RMS is 180, the current, keep this in mind, leads the voltage by 37 degrees. Okay. What is the total resistance of the circuit? And then B, calculate the reactance. And I think they mean total reactance. They don't say reactance of the inductor. They don't mean the reactance of the capacitor. They say the reactance. And so the combination of the L and the C together. So we're not going to be able to find them individually, which kind of makes sense. I think we would need 3 equations to find those 3 unknowns. And it sounds like they've given us enough to get 2 equations. So we need to think of this as one unknown and the other one being the resistance. So, in other words, the one equation, which you've been seeing throughout this video, has been the current is equal to the voltage over the impedance. And in this case, the impedance includes a resistor and so let me think of this as one unknown. This is the total reactance, the combination of the inductor and the capacitor. So, since they give me these numbers, like the current RMS is 9 amps right here, so here's the 9 amps, and they give me the voltage of 180, then this is the square root of R squared plus, and again, I'm tempted to maybe write this as one variable, because, again, when it's written like this, it almost looks like there's 3 variables here. But I want you to think of this difference as being what they are asking for here in part B, calculate the reactance of the circuit. And they say the 2 together. So that's kind of my first equation. In fact, they gave me some nice numbers to work with. If I divide here by 9, that gives me a 20. And if I move this to the other side and square it, I get R squared plus this XL minus XC squared equals, and 20 squared is 400. So here's my 2 unknowns. And then, of course, this 400. Now, the other thing they gave me is the angle between the current and the voltage, and they tell me which one leads. The current leads the voltage. So if you go to our phasor diagram we've been working with, and you have to kind of picture these as what might make a good stick. Oh, I know. Got this broken mechanical pencil here. But thinking of this as our phasor, we can spin this around. And so if we are looking at the voltage, maybe it would stand out if I did a different color than my grid. If we did the voltage from the resistor, it would be something like this, and then spinning around. And if we did the voltage of the inductor, it would look something like this, and then spinning around. And then if we did the voltage from the capacitor, and here's where I'm going to pause, come back here. And notice they say the current leads the voltage by 37. Okay, so the current is in the same phase as the voltage on the resistor. So thinking of this as the current, the result of all these three, and so the capacitor is going to be something like this. But I know that this one is the capacitor. It's going to be a little bit bigger in its voltage because the result is angled 37 degrees. And in my picture, I'm going to put the voltage total, maybe we'll even call it max, at 37 degrees behind the current. Because again, they make it very clear, the current leads the voltage by 37 degrees. And so I know in class I drew one where we had it going up into the first quadrant. So the current was lagging behind the voltage. But here, the current leads the voltage, meaning that the capacitor is stronger, or this line is bigger than the inductor. All right, so what we said then is this being the voltage on the resistor would be IR, and the length of this vertical piece is actually the voltage on the inductor and the voltage on the capacitor fighting each other. And so this right here becomes, and we usually write it as XL minus XC times I, meaning it's pointing down. We would have a negative number. The voltage on the capacitor is a little bit more. Okay, and that's why we had this phase angle, which we said tangent of the phase angle would be the opposite, so XL minus XC over the resistor. And in my case, that would be the tangent of negative 37 degrees. Oh, and let me go back to my red, and now I'm doing equations here. So I would call this my second equation to match with that equation. So let me get a new page here and kind of write down my system of equations. So I've got this r squared, which I'm trying to find, plus this other unknown. And now I'm just going to write that as one variable. Why don't I just call it, for lack of better options, it is a reactance, but I don't want to call it R for resistance. So I'm just going to call it a U squared, and that's equal to 400. So that's this first equation. And now this next equation that we just worked out is saying that we have a U over an R. So U over an R is equal to the tangent. Let me just get a number here. But I believe I'm still in radians from the last problem. Yeah, so got to be a little careful here. Go back to degrees. Okay. And so this is the tangent of a negative 37 degrees. And so that is a negative 0.573. Okay. And then maybe I'll just solve for U squared by bringing the R to this side and squaring it. And so this would be 0.568 R squared. And I will use that in the first equation. So this is R squared, and in place of U squared, I'll put 568 R squared equals to 400. And so 1.568 r squared is equal to 400. Or, doing a little bit of work here, let me just add 1 to that and keep that handy, because this is then 400 then divided by my last answer. That would be r squared. So then I can take the square root, and it looks like 16.0 ohms if we're looking at 3 significant figures. Which then I can get my U, which is the reactance, the XL minus XC, by using maybe this equation or that one, but this one looks a little bit easier here. And so I'll take my 16 roughly and multiply it by that negative 0.753 and get a negative 12.0 ohms. And good, I got a negative here, meaning that the capacitor is stronger, which of course matches our diagram here, is stronger than the inductor in terms of this particular frequency, whatever frequency that is at, and they don't really say. But anyways, I think I've answered the question. What is the total resistance? Got it. And then what is the reactance of it? Got that too. All right, good. Well, that went a little bit faster than planned, way under an hour, but hopefully those were helpful, and I'll make another 4 in a little bit. Take care.